Hey everyone, I'm Mr. A, and today I want to talk with you about vector equations in 2 dimensions. If you don't know what a vector is, or a vector equation, then you're going to need to look at that before you watch this video. So in this video we're going to take a look at this problem. This is a problem that I wrote, and there's a lot of work to get into the problem first. So what I'm going to do is break this video into 2 parts. In this part I'm going to start with the vector equations, and then we'll just do the work as far as computing distances and things like that, and all the vector mathematics that we can do here. I'm going to make a second video, which I'll link to right below, so you can click on that to watch that video, where I develop those vector equations and actually go through the problem and pull all the information out and figure out the equations. So I strongly recommend that you either pause the video or go watch the video of me doing it, or maybe both, so that you get these equations, because it's a real good process to go through. But I'm going to here start with the equations for you, and we'll actually just jump right into the problem. So here are our 2 vector equations. This is the Aberdeen-Fisher, and I'll just group that together, and our Bandit. And these equations are what we're going to use to answer all the different questions about these 2 ships. So let's see, let me just go ahead and take these to the next page with me, and here's the first question we're going to ask. Which ship is traveling faster, and by how much? Assume constant speed. Now if you read through the problem, you actually know that we know the velocity for the for the Bandit already. The velocity here is is exactly 5 meters per second. That's easy to see from the velocity vector, right? Because the components are -4 and 3. So the square root of -4 squared plus 3 squared is of course 5. And that's where that 5 meter per second velocity is coming from. To get the velocity for the Aberdeen-Fisher, let's just go ahead and put a B there for the velocity of the Bandit. To get the velocity of the Aberdeen-Fisher, what I'm going to do is take the square root of the components of its velocity vector, right? So this is the vector that tells me how much the ship's position changes per unit of time. So that's my velocity vector. And if I find the magnitude of it, the square root of 2 squared plus 1 squared, then of course I'm going to get radical 5. Now, radical 5 is not the same as 5, right? Radical 5 is much smaller. Rad 5 is much smaller than normal 5. So this tells us that the Bandit is moving faster, right? The Bandit is moving faster. By how much? Well, by the difference between these two, right? By 5 minus rad 5, whatever that quantity is, meters per second. Okay, so the Bandit is moving faster by whatever the difference between 5 and rad 5 meters per second is. Just quickly to show where I'm getting this mathematics from here, if I have the velocity vector, this 2, 1, I can think of a triangle, and this ship is moving to the right 2 and up 1 every unit of time, right? And so of course that's a right triangle, and so you can simply use Pythagorean theorem, and your velocity is going to be the hypotenuse. That's the magnitude of that 2, 1 vector. Okay, so that's what's going on here. That's where I'm getting this square root of 2 squared plus 1 squared from. That's the rad 5, which is the velocity of that ship. So hopefully that makes sense. The next question we're going to ask here is, if both ships maintain a constant velocity and heading, will they collide? So I'm going to again start by looking at the equations for the 2 ships, and let me just center that a little better there. Okay, so here's my 2 ships. When I'm looking for the distance between the ships, I actually find it more helpful to work in a parametric form. So I would think of the position of ship being, the position of ship B, the Bandit, being 2000 minus 4t, comma, 3t minus 999. Right? So think for a second about why that's the case. All I'm doing is rewriting that vector equation in terms of x and y, right? So my x coordinate is 2000 plus t times -4. That's all I've got there. And my y coordinate is -999 plus t times 3. I wrote that as 3t minus 999 because I don't like to have a negative sign in the front. Those leading negative signs get lost pretty easily. Okay, so what about my Aberdeen-Fisher? Well, that ship's position is going to be 2t minus 1000. Notice how I got rid of that leading negative again, comma, 100 plus t. And that you could write t plus 100 or 100 plus t, whatever makes you happy. So these are the positions of the ships as a function of time. In other words, the parametric position of both of these ships. If I want to know how far apart they are at any given time, all I need to do is consider a right triangle where I place one ship at one corner and the other ship at the other corner. So let me place the Aberdeen-Fisher up at the top here of my triangle, and then I'll place the Bandit down at the bottom of my triangle. And then all I need to do in order to, I'll just put it over there, right? All I need to do is calculate my delta x and my delta y. So this would be the delta x, the change in the x positions of the two ships, and this would be my delta y, the change in the y positions of the two ships. So let's start with delta y. I've got 3t here, and I've got just 1t here. So I'm going to do 3t minus 999, and I'll subtract 100 plus t from it. So that's 3t minus t. That gets me 2t. And negative 999 minus another 100 is minus 1099. Right? So all I'm doing here is just taking the difference in the x-coordinates and the difference in the y-coordinates. So that's the difference in my y-coordinates. Right? 3t minus t and negative 99 minus 100. How about my delta x? So my delta x, now I'm going to look at my x-coordinates, 2000 minus 4t, and 2t minus 100. Now this time, I want to have a positive t, so I'm going to start up here with the 2t, and I'm going to subtract the negative 4t. Now you might be thinking, hey, Mr. A, you got to go in the same direction. If I started here and I subtracted this one, then I have to start here and subtract this one. But if you think about what's about to happen, I'm going to plug in the Pythagorean theorem. Everything's getting squared anyway, so the order doesn't make any difference. It's only going to affect the SIGN of my answer. So to keep everything nice and positive t's, I'm going to start here. 2t minus 4t, well, that is 6t. Negative 1000 minus 2000 is negative 3000. And there you go. There's my delta x and my delta y. So my distance between these two ships for any moment in time is just the square root of, right, my delta x squared, which is to say 6t minus 3000 squared, plus my delta y squared, which is 2t minus 1099 squared. Now you can distribute that out and turn it into a quadratic. If you do that, what you'll find is that when you simplify, you get the distance is the square root of 40t squared minus 40,000, 396t, plus 102.07.801. Now, you don't need to do that. You could just plug this into a calculator and ask it to find the minimum value, but I think it's nice to see that this is actually a quadratic, and it's going to turn around. The turning point is going to happen at negative b over 2a, which is to say, at t equals 40,396 over 2a, which is 80, I'm going to get a minimum point because this is a quadratic that opens up. So that's going to be a t-value of roughly, let's see, 504 point, well, exactly 504.95, which is, real close to 505. Let's just go ahead and make that 505. And if you plug that value into the equation, what you'll find is that the distance is, let's see, comes roughly out to 94 meters. So about 94 meters is the closest you get. So this is the closest you get. And it happens at about, well, it's 505 seconds, which is like 8 minutes and 25 seconds. So it happens at about 11:38 and 25 seconds. Okay, so there's my closest distance between these two ships. Happens at about 11:38 and 25 seconds. That means there is no collision. Right? So let's take a look at the next piece of this problem here. Now we're going to go between what times will the ships be within 300 meters of each other? Okay, so in order to answer this question, we're actually going to use the work we did a moment ago. We already figured out over here an equation that tells us how far apart the ships are for any moment in time. So let's take that equation, carry it forward. What am I looking for now? I don't want to know when they're, how far apart they are. I want to know when they're 300 meters away from each other. So if I just go ahead and set this equal to 300, well, that means that 9 0,000, so 90,000 is equal to 40t squared minus, this whole thing for 4396t plus 102.07.801. And hey, that's a quadratic, right? Just bring the 90,000 over, you can plug in the quadratic formula, and what you'll get with the quadratic formula is you will come up with two values for t. You will get t is approximately equal to, let's see, 459.900, so you get about 459.900, and t is approximately 549.900. 0.9997. And so let's just go ahead and round those a little bit. Let's say, all right, we're basically talking about 460 seconds and basically talking about 550 seconds here. So in between these two times, what's going on? Well, remember, the distance is given by a quadratic with a positive leading coefficient. So if we were to think about the graph of this quadratic, it's going to open up, right? What did we just find when we found these two values of t? We found the points when at time 460 approximately and time 550 the ship is less than 300 meters apart, and the rest of the time, of course, they'll be greater than 300 meters apart. So the ships are less than 300 meters. Sorry, that kind of looked like an angle sign, right? The ships are less than 300 meters for about, oh, what is it, 90 seconds, right? Between t equals 460 and t equals 550. And of course you can convert that to time by just adding to 1130. For the sake of time in this video though, I'll let you do that on your own. I'm just going to move on to the next part of the question. So in part D, we want to know what's the closest each ship will come to the radar station. When will this occur? So for this, we need to think about a picture a little bit. So the radar station, that was at 0, 0, or at least that's where I placed the radar station. It's a nice, easy place to put it. So let's go ahead and drop the radar station at 0, 0, and I'll draw that right there. And I'm going to create a path for my ship. So let's first start with the Aberdeen Fisher. And we'll just do this on two separate slides for the two ships. So if this is the Aberdeen Fisher, what I want to find is I want to find the point that makes this vector perpendicular, right? That'll be my closest distance when that vector is perpendicular. So what are the coordinates of any point on the Aberdeen Fisher's line here? I'm going to be at 2t minus 1,000, comma 100 plus t. Now this point here is 0, 0. All right. So what I want to do is I want to figure out the vector that takes me from 0, 0 to this point. Now because it's 0, 0, that's really easy to do. The vector is just 2t minus 100 minus 0, right, my change in x, and 100 plus t minus 0, my change in y. In other words, that red vector is simply 2t minus 1,000 and 100 plus t. That's the red vector. Now for the blue line, I don't actually need the entire line. All I need is the direction it's going. So what direction is that line going in? It's going into 1, right? That's the vector that tells me what direction that ship is traveling. And if you flip back to the equation for the Aberdeen Fisher, right, excuse me, the vector equation, that's that velocity vector. It's the direction of travel for the ship. So I can take that to 1, and all I'm going to do is simply dot that with the red vector. And when that is equal to 0, and we'll find the time that makes these two vectors perpendicular. So if you go ahead and do that, we get, let's see, make sure I'm black here, we got 4t minus 2,000 plus 100 plus t equals 0. And so that works out to t equals 380. And then if you go ahead and plug that in, so like that's the time, excuse me, I wrote 30, time equals 380. And if you go ahead and plug that in, then what you'll find is the distance. Now, what do I plug it into? Well, the distance between these 2 points is simply the delta x and the delta y, again squared, right? So my delta x is going to be squared, and I'm going to add that to my delta y squared, just as we did on the last screen. Now, what is my delta x and delta y? Well, they're actually really easy to compute because this point is 0, 0. So the change in x is simply 2t, right? 2t minus 1,000, that is my delta x, so 2t minus 1,000. And the delta y is just 100 plus t. Except, of course, I'm not going to plug in t, I'm going to use t equals 380, right? So when t equals 380, then what you get is the distance is approximately 536.7 meters. So that is the minimum distance that that ship, the what ship are we talking about? The Aberdeen Fisher, is ever going to come to the radar station. And it will happen at time 380. Now we're going to ask the same question about the Bandit, the other ship. And to answer that, we're going to draw a similar picture, but this time with the Bandit. Now the Bandit is coming in this general direction. Right? And we're going to do the same thing. We're going to look for this vector to be perpendicular. So I'm trying to make a right angle there. Now the equation for the bandit, so right here is my bandit equation. For any given time, I can figure out exactly where the bandit is by looking at 2000 minus 4t and 3t minus 99. So we're going to start by creating this red vector. This red vector here is going to be the difference, the change from 0, 0 up to the position of the bandit. Well, since I'm starting at 0, 0 again, that's really easy. The x position is just 2000 minus 4t, right? 2000 minus 4t, and the y just is 3t minus 999. Okay? So this vector describes this red line right here. This is this vector going from 0, 0 to the position of the bandit for any moment in time. And then what I'm going to do is I'm going to take that vector and dot it with the vector that tells me the direction that this ship is going. All right, so what's the direction of the bandit? Well, it's moving left 4 and up 3 each time a second elapses. So this is the vector that tells me what direction the bandit is going, right? Negative 4, 3. And notice again that if we flip back to the page with the equations, we can see that that is the velocity vector of the bandit ship. That's the vector that tells me the direction the thing is going. So now we're just going to go ahead and dot these, and as before, we're going to set that dot product equal to 0. So let's see, what do we get this time? We have 16t minus 8,000 plus 9t minus 2997 equals 0. And if you work that out, we get, let's see, 25t is equal to 10,997. So t is approximately, it doesn't work out nice this time, 439.88. So that's awfully close to 440 seconds, right? And to calculate our distance, again, I'm simply going to think about the distance between 0, 0 and this point right here. But since, again, I know my x-coordinate and the position here is just 0, 0, this is a very simple distance. The change in x is simply 2000 minus 4t. I'm going to square the change in x. I'm going to add to that my delta y, which is, again, since I'm going from 0, 0, simply 3t minus 999 squared. Now I'm going to evaluate that at, t approximately 439.88, and what I'll get is that the minimum distance occurs at t 439 and is about, let's see, it's 400.8 meters. So that is the closest that the bandit is ever going to come, right? This is the bandit. And perhaps I should have labeled that on the last one, so let me just pop back. This is the Aberdeen, right, Fisher. And so there's our minimum distance and occurring at time 439 approximately 0.88. Okay. Now these are pretty simple because the radar station is at 0, 0. So that's nice, right? It makes these vectors easier to figure out. It makes the distance easier to figure out. But what if we move from 0, 0? That's what the next position says, or the next question. So we have this weather buoy now. And the weather buoy is 50 meters west, 610 meters north of the radar station. So let's start by noticing that that means the weather buoy is at a position negative 50, 610. So let me just go ahead and draw in here, and I'll call this point negative 50, 610. All right. Now, federal regulations prohibit the ships from passing within 50 meters of a weather buoy. Will either ship need to alter course? In other words, is either ship going to come closer than 50 meters to the weather buoy? So let's begin as we did last time. I'm going to sketch out a path for the Aberdeen Fisher, and let me again go grab the coordinates there. So the Aberdeen Fisher, oops, let me grab the coordinates for the Aberdeen Fisher. Okay, and just take that over here. All right, so the Aberdeen is going to be at those coordinates all the time. And we're going to think about the vector that connects the weather buoy to the Aberdeen Fisher's position. And again, we want to make that perpendicular to find the minimum distance that's going to happen between that ship and the buoy. Now you may notice that I just drew this to look like the last picture. I'm not really concerned with whether this ship is actually passing above or below or to the left or to the right of this weather buoy. I just want a picture to help me visualize what's going on. So again, I need to create that red vector. Now the red vector, this time it's not 0, 0, so I have to work a little bit harder. How do I get from this point to this point? It's just the delta x and the delta y between the 2 points. So for the delta x, I'm going to look at 2t minus 1,000, and I'll subtract negative 50. So what's that going to get me? Well, 2t minus 1,000, but then I'm going to subtract the negative 50, which means I'll end up adding 50. Right? That's all. That's all I got to do. What about my delta y? Well, for the delta y, I'm going to look at my y values. Now here I have to do it in the same direction because I'm not squaring anything. We're not working in Pythagorean theorem. So I have to again start at this point and subtract this one. So that's 100 plus t. Oops, I want to stay red. 100 plus t. And I'm going to subtract 610. That vector is going to be dotted, just as it was last time, with the direction, the velocity vector of the ship. So what direction is it heading? It's still heading in 2, 1. It's the same ship, same problem as before. So we'll go ahead and set that equal to 0. We can simplify this a little bit, right? What do we have over here? Really, it's 2t minus 950, right, being dotted with t minus 510. And so we're going to dot that with our 2, 1 doesn't change, right? And we simply set that dot product equal to 0. So when we do that, we get 4t minus 1900 plus t minus 510 is equal to 0. Well, that gives us 5t equal to 2410, and that gives us t equals 482. Nice round number. I'm going to just scooch all of this over to the left because I'm going to run a little short on space on the right hand side. So this is the time when the minimum distance occurs. Now I need to figure out what is that minimum distance. For this one we have to work a little bit harder. So the distance is still going to be the square root of my delta x squared and my delta y squared. But what is delta x this time? Well, it's the difference between this point and this point's x coordinates. But we already figured that out, didn't we? That's this number right here, right? The 2t minus 950. So I'm just going to pop into there, 2t minus 950. And I'm going to add to that the square of the delta y. And again, delta y is the difference between that coordinate and that one, which we've already figured out. It's t minus 510. So that's all I need to do to work out my distance. I'm going to plug into that distance formula, but I'm going to evaluate it not just for any t, but just at t equals 482. And what I'll find is that the minimum distance ends up being about 31.3 meters, which of course is less than 50 meters, right? So that means that this vessel will need to change course. It is going to come too close to that weather buoy. Okay. So notice this is very similar to the work we did in this problem where we were finding how close it came to the radio station. The only difference being that since this was 0, 0, the vector was really easy to work out. Now that it's not 0, 0, it's negative 5610, I just have to take that into account when I do my delta x's and my delta y's. Everything else is the same. So we're going to look at this problem one more time, but now for the bandit. So the bandit, once we want to find out how close the bandit comes to this same weather buoy, and once again, the bandit is going to be traveling along some direction. I'll draw the bandit this way. I don't know if it passes to the right or the left, and I really don't care all that much. I just want to find this minimum distance. Let me go ahead and grab the equation for the bandit. And so the bandit's equation is right here. So here's our bandit, right? 2000 minus 4t, 3t minus 999. So again, I need to calculate this red vector. So the red vector is how do I get from here to here? Okay, so you should be seeing where this is going now. 2000 minus 4t minus negative 50. So that's 2000, I'll write it out long, minus 4t minus that negative 50, so plus 50, right? That's a 5, 0. And then the y's, 3t minus 999, 3t minus 999 minus the y value, 610. And just as before, we're going to simply dot that with the direction of the ship's travel, this blue vector, right? So what's the blue vector? Its direction anyway is negative 4, 3. That's the velocity vector of the ship, negative 4, 3. Dotting that and setting it equal to 0 is going to give us what we need. So we can simplify this just a little bit. Let's see, what do we end up with here? We've got 2050 minus 4t, and then we have 3t minus 1609. And we're going to dot that. We're just going to do this to it, right? So we'll dot it with that. I'll just carry that down. And when we go ahead and do that math, what do we actually end up with? 16t minus 8,200 plus 9t minus 4827. That's still equal to 0, which means t ends up being about this time, let's see, about 521 0.08. Okay, so again, that's the time when the ship is closest. Now I need the distance. So my distance is the square root of my delta x squared and my delta y squared. But again, I already calculated that, right? That's what this red vector is. It's my delta x and delta y from that buoy to the ship's position. So all I need to do is plug in with 2050 minus 4t squared plus 3t minus 1609 squared. I'm going to evaluate that all at t about 521.08, and I will get a minimum distance of about 57.2 meters. So that is, of course, greater than 50 meters, right? So that means that the Bandit is fine. Bandit can maintain course. Okay, so I hope you found that useful, and I hope that answers some of your questions about vector equations and applications. There's a lot of stuff going on in this problem, so certainly feel free to rewatch the video. If you have any questions, please feel free to ask. If you're in my class, you can just ask me, or you can message me through YouTube. And if you enjoyed this video, please give it a like, subscribe to my channel, feel free to leave a comment below, and as always, have a great day.